Hi everybody, hi. Mike here, and we're going to continue our series on Lewis electron dot structures. Let's continue and pick up, oh by the way, my egg, my robin egg didn't make it. I'll have to show you that. Anyhow, picking up where we left off last time, where we talked about fluorine, F2, all right? One of the things I want you to feel soothed about is that if you do any of the diatomic molecules, which is one of the stable ways the halogens can occur, all down the group family, they all bond in the same fashion. They all enter in to this agreement of the bond with 7 valence electrons. They all have a total of 2 bonding electrons and 6 non-bonding electrons each. By the way, we're going to talk about more diatomic molecules, but hydrogen would kind of fulfill its octet rule in a different way because it's in the first period and only needs 2. By the way, if you ever need a quick memorization of how to know which elements that are nonmetals occur as diatomic atoms, it's have no fear of ice cold beer. All right, and you can substitute berries or something if you don't like the thought of beer. All right, I like it. The thought. Oh, okay, so then we've talked about that one, that one, that one. We've got 2 more to explain. Let's talk about what happens when oxygen atom meets other oxygen atom. They, of course, have 6 valence electrons. I'm going to draw it this way just to show you that you can't do this matching thing. It leads you to the wrong conclusion. So, you know, we're going to go ahead and say that you add up the valence electrons. There's 6 each, so 12, and then you make as minimum number of bonds for it to stay together. So if I did that, if I made 1 bond, it would not have enough electrons. It doesn't have its 8. So guess what happens? They have to share more. And this is where we get into double bonds. So you can have 2 pairs of electrons. So these would both kind of kick in. And that is a double bond. All right, so 2 oxygens would share via a double bond. Let's go and talk about nitrogen. Now my kid's coughing. She has allergies, so don't worry. I'm pretty sure. So then let's talk about nitrogen. Okay, so what happens when 2 nitrogens meet up with each other, having 5 valence electrons? Everything needs 8. They would have to kick in 3 electrons each into a triple bond. All right, everything, remember, you can always go around and count. 2, 4, 6, 8. Dash counts as 2 electrons. It's just shared between the 2 atoms. All right, now I know what you're probably thinking is okay, let's go 1 over. And now you, whoops, see, my subconscious made me slip because I felt like I was doing the wrong thing. I've seen that this has been reportedly possible, but doesn't happen. All right, so we go up to triple bonds, and then nature starts to say, hey, there's a little too much going on here between 2 atoms, and there's not enough ways for those orbitals to overlap, to make a long story short. All right, now what happens next when we kick it up a notch of difficulty? And we say, instead of just 2 atoms, we're going to go to a compound. So, good compound to start with would be like CH4. All right, now let me tell you what ain't going to happen. First of all, just like before, what we're going to have to do is we're going to have to add up valence electrons. Carbon in group 4, 4 valence electrons. Remember, not total atoms, but valence. 4 H's. Be another 4 valence electrons. So how are we going to distribute those 8 valence electrons? Well, let me tell you what ain't going to happen. All right? What ain't going to happen is they ain't going to make like a conga line, you know, like you see at a wedding or something. By the way, there goes already 2, 4, 6, 8. There goes our 8 valence electrons already. And I've not only not given carbon enough valence electrons, it's only got 2, but I've also kind of perverted hydrogen into exceeding the octet rule. And so it only needs 2 to fill up that first quantum level. So what's going to happen, folks, is somebody's going to have to become the central atom, and the others are going to have to sort of stem off that central atom. And so there's some rules. They're pretty simple rules, but let's talk about what happens next. Okay, folks, the next step in the game is to figure out who goes in the middle. So the first step of a Lewis structure is to figure out who's going to be the central atom. Cool. So there's a bunch of rules, and some of them, you know, are more important than others. The first rule is that it is never hydrogen. Well, that solves the problem for this particular example, but I'll keep going. The other rule is it's usually the atom with the lowest electronegativity. All right. And then there's some sub rules in there, but we'll talk about that. So you know what? Bang, got to that one. So what's going to happen is carbon's going to go in the middle. That's step 1. Step 2 is that you've got to add up all the valence electrons. That's what we did in the previous example. So let's go ahead and do that. Carbon, 4 valence electrons, group 4, 4 H's, 4 valence electrons. We're playing with a total of 8 valence electrons. Okay, step 3 is we're going to put this thing together with the central atom and the outside surrounding atoms, and we're going to create what we call a skeletal structure, which is we're going to form, I'll call it make, minimum number of bonds. That's going to be minus 2 electrons each. So let's go ahead and do that. Except I have to cough. Okay, I'm back. Thanks, allergies. So what we're going to do is we're going to put carbon in the middle, hydrogens on the outside, and we're going to go ahead and make 4 bonds. So back to our total here. That's going to be 8 valence electrons minus 8 valence electrons for making the 4 bonds. We fulfilled half of the goal is to run out of valence electrons or utilize them, and the second goal of doing a Lewis or forming a Lewis structure is we've given every atom a filled shell. Now watch out, the first shell only holds n equals 1 only holds 2 electrons. So we've given carbon a full octet of 8 valence electrons, and we've given this hydrogen and that hydrogen a filled shell of 2. And so we have made a successful Lewis structure, and that's what it looks like on paper, but as you find out later, we're going to find out that that is a 3-dimensional shape to it. And so let's talk about a more complex one. Okay, here comes our next example as we go and amp up the complexity here. Now, I want to address something. We'll call this, this is the wrong thing. This is a little corner of shame where we're going to do something wrong, okay? I have some of my students who say like, okay, look, can't I just map all this out and do this kind of thing? Let me see, like that. I'm putting 6 valence electrons around. And you know what? You can do this if it's simple and doesn't involve double bonds, in some cases just single bonds. But you can say, yeah, I'm going to just go ahead and I'm going to do this. I'm going to do that, and there's one bond. And then I'm going to do this, because I'm going to just match up all the single electrons. And so this is going to look like a triangle. Like that. And that, my friends, is what we call in science perversion, because that will not happen. That ring won't happen for reasons we're going to talk about later. So let's quarantine that like a virus and keep going through these steps, although they're boring, for how we're going to make a Lewis structure of SO2. So we go back to the rules. I know rules aren't fun, but number one, who's going to go in the middle? The one with the lowest electronegativity. There's no hydrogen in here. Sulfur's 2.5, oxygen's 3.5. Sulfur's going to go in the middle, central atom. It's usually also the one that's outnumbered. All right? So that's usually for a reason. We're not going to get into anything too complex today. Same step. Add up valence electrons. Sulfur's in the same family as oxygen, so sulfur's got 6 valence electrons, 2 oxygen, 6 each. It's got 12 valence electrons. We're playing with a total of 18 valence electrons. So now we're going to lay it out in the minimum structure that we need to make. And we're going to make as the minimum number of bonds possible, which in this case, to hold it together, is going to be 2. So we're going to go ahead and we're going to say, okay, minus 14 electrons. Then we're going to see if we have an octet for everything. And it's going to turn out we don't, because we need 6 electrons here, because it needs 8 and it's got 2. Dash is 2. 6 electrons there. We need 4 more, because it's got 4, 2, and 2. Everything here needs 8 and 6 there. So 6 and 6, there's 12 and 4. We need 16 electrons. We only got 4. So what we need to do is go to the next step. I guess we call that step, I'm afraid to write a number. We're going to need to go and reevaluate now. And we're going to go ahead and see if we can make more bonds. So make additional bonds. Now I want to stress this, because this is a weird example and I want to protect you folks against weird things that could happen. We're going to just make a bond at a time. And then we're going to retry the step where we distribute them. So it turns out it doesn't matter where we put this, left or right, and there's a whole big bunch of theory we could go into on that. So we're going to go ahead and make a bond there. That's going to take away 2 more valence electrons, leaving us 12. And then we're going to find out that we can distribute those 12 to give everything a full octet. We could put 2 there, there's 4. Put 2 there, that gives it 8 now. 2, 4, 6, 8. 2, 4, 6, 8. And then we could put 6 there. 6, 2, and 4 is 12. Game over. We just made the Lewis structure in 2 dimensions of what SO2 looks like. Is it weird? A little bit. And actually what you can find out is, though, remember how we were short some electrons? The number of pairs tells you how many more double bonds you have to make. So now I'm going to go and tell you what happens. This would be like the wrong thing all over again. People will like say, I'm going to make 2 bonds, and then you free up more electrons than you need, and then what happens is I end up getting this when people turn their tests in, you know, so they invent like the quintuple bond, you know, because they just keep going past the sweet spot, and so don't do that. I just totally wrote on the wrong. Sorry. Well, that's good that I did that, because I was filming it wrong while I was doing the wrong thing. Don't do that. Okay, folks, we have done 2 very different examples of a Lewis structure with a central atom and surrounding atoms. One had just single bonds, the other had some double bonds, and we're not done yet. We're going to pause there to let you try some simple ones. I will pick up with another example next time, and then we'll have to start talking about what happens when atoms cheat the octet rule, because the octet rule is an important rule, but some atoms just can get away without following it. So we'll talk about that next time. Hang in there. Take care of yourselves. Now check this out. These things, that egg, boop, look at, look at. And then like, you can really tell that there's nothing that was, there's no embryo in there. And so I don't know what happens. I'm not a robiniatrist, but I guess what happened is maybe the bird just couldn't hold it anymore. You know, you ever do that? Like, you ever eat a whole bag of dried apricots? Oh, dang. I broke it. Okay. See you later. Bye.